Let's look again at the histogram from the previous activity. You'll remember that it represents a summary of the frequency with which each score occurred. If you overlay the histogram with a line of best fit, the shape of that line represents what is known as a normal distribution. The normal curve represents the distribution you would expect when large numbers of random factors can influence a score. It is a hypothetical, bell-shaped, symmetrical distribution of scores. The terms normal distribution, normal curve, and bell curve are often used interchangeably. The normal distribution is a symmetrical curve with a bulge in the middle and tails to either end. The majority of the population will fall within the average range, represented by the bulge in the middle, and with greater variation falling at either end. Many human attributes, characteristics, and aspects of performance fit the profile of the normal curve. For example, height and weight are normally distributed. If we surveyed a large number of people, we would begin to find that the majority of them, in terms of their height and weight, will be within the average range and fall within the bulge of the normal curve. People whose weight and height deviate from this, i.e. they might be taller than average or weigh less than usual, will be placed at either end of the normal curve. Perfectly symmetrical distributions rarely occur in real life, but the greater the number of participants in a test, the closer and closer the distribution gets to the normal curve, so long as the data is distributed normally. The assumption underlying the construction of psychometric tests is that they are measuring attributes that are normally distributed. Tests don't accidentally become normally distributed, so to make the data work, the test has to be manipulated to ensure that it fits a normal distribution. This process is called standardization. Well-constructed tests use large standardization samples to make sure that, as far as possible, tests reflect the normal distribution present in the population. To illustrate the effect of increasing sample size, imagine that you measure the heights of everyone you know and plot them on a histogram. There will probably be a few at the extremities and many in the centre. And even if you do this for 30 people, there will be slight anomalies. If you happen to know a lot of tall people, there will be a bump at the top end of the graph that should not be there. But if you increase the sample size and include people you do not know, then the bumps will start to be smoothed out. If you measure and plot the frequency distribution for 1,000 people, then you will move closer still to the perfect curve. Medical authorities that assess growth in young children use charts and graphs based on data from thousands of children. In these, the distribution of height is so close to the normal curve that you wouldn't know the difference. Some data is not distributed normally. This results in graphs that are not symmetrical. This type of distribution is said to have a positive skew. The tail of the distribution is longer on the right side, which means that the results on the right-hand side of the distribution curve are further away from the midpoint than the results on the left-hand side. The opposite is true of a distribution with a negative skew. Here, the results on the left-hand side of the distribution curve are further away from the midpoint than the results on the right-hand side.